Thank you very much, everybody, for coming to this session. I'm Andy Vogelman, and I will be presenting on behalf of the team on the observational parts and also the data bundle selection. So what you're going to learn in this section is how we selected our shallow convection cases, the observations that we use for simulation evaluation, and then the skill scores that basically combine the observations and the model outputs so that we can rank the quality of the simulations. And then finally, the Lasso bundle browser is the best port of entry, so to speak, where you can find, sort, and order the simulations that you want. So first, shallow convections cases. So as Bill mentioned, we only run for shallow convection days that we select. This is not an NWP product where we run all days. Doing that selection, there are many details, but just as a broad overview, they are manually selected by Bill and myself, involving several criteria. First, of course, is that shallow convection clouds need to be present over the Southern Great Plains Central Facility. To make that assessment, we use many different observations, which I don't have time to get into right now. Second thing is that we want to see cloud uniformity across the domain. And this is particularly important with regards to the forcings. So this is just to give you an example. We use the GOES visible imagery, and you can see that there's a very nice shallow convection field, but over the SGP, but basically it dissipates to the west of it. And so this is an iffy case that even though you have clouds at the SGP, it's not 100% clear that the forcings, the atmospheric forcings, will be able to capture the moisture and temperature tendencies properly. Finally, we want to make sure that there's no widespread precipitation, like pop-up storms in the area. And that for that, the best thing is to use the NexRad. And the last item is that we have critical measurements, particularly the 12Z sounding that we use to initialize the model, liquid water path, and other measurements that are critical to the model evaluation. If you put all that together, we have 95 case days, a total of 95 case days over the last 5 years. Now, remember when Bill was discussing things, that we at least have 8 simulations per day, and that alone would give you 760 simulations. There are additionally some other simulations that we did for sensitivity studies, or for instance, using SAM simulations as well. So we have in excess of 760 simulations to work with. Now, the question is how do you find the simulations that are of interest for your research? And that's where the skill scores come in. And I'll be describing these in a little bit more detail, but the skill scores allow us to rank the ensemble simulations, depending on what variables are of interest to you. One might say, well, any LES simulation is valid, right? To some extent that's true, provided that the model is properly run and the model physics is okay. But something that an underlying principle that we really want to emphasize with Lasso is that we want a statistical library of representative cases for study. We're not interested in grabbing the one canonical case, and we also do not want to be focused on outlier cases as well. So this is the best approach in our view for providing essentially what nature is really doing. So to get into the observations now, I first want to say something about what I'm calling data scales. In other words, what sort of region is a given observation measuring? The most localized is the point or pencil beam scales. This could be an in situ measurement such as surface temperature, or it could even be a column observation that we get from the Ka arm zenith radar or KASER. Okay, so in the case of the KASER, it's a pencil beam that's looking up, and clouds are advecting through it. So you can get the valuable information, but it means that you may have to integrate longer in time to capture statistics that are relevant to the model. the time goes down as you start broadening this out. And so what I'm calling local observations are things like the hemispheric view that you get from the total sky imager, or a new product called COGS, which stands for Clouds Optically Gridded by Stereo. What the COGS is that it's a number of stereo cameras that are used to detect the position of cloud base and cloud height, as well as cloud fraction. And both of these local observations give you an area that's approximately a 3-kilometer radius around Earth, or 6-kilometer diameter around the SGP. You have regional networks now expanding out even further. And the first example is the Doppler LiDAR network. We have 5 different Doppler LiDARs. They are located approximately a 45-kilometer radius around the SGP. What they do is they give you information on vertical velocities, but also what we do is we use it for cloud-based heights. And below is an example of the cloud-based heights versus time for all of these different sites for a given day. I will point out that this day I could have picked one where all of the observations beat up very nicely, but I just kind of wanted to show this as an example, in this case of extreme variability. And how this is going to be reflected is it's going to increase the standard deviation in the observational fields that we use. Above, I'll note that there's a topography map there. And it looks a little scarier than it actually is. The height range is plus or minus 100 meters, but probably more significantly is that there's a tendency for things to be moister in the southeast corner. And I would argue that that actually seems to be more of the reason for variabilities that we see within our domain. And the last regional network is our MET stations that we have both from ARM and also the Oklahoma Mesonet. And we basically use things that are within a 60-kilometer radius around the central facility, which is the red dot in the center. And we use them to, for instance, compute things like lifting condensation heights, level heights, like shown in the plot. Again, this is for the same day. So this is an example of extreme variability where the standard deviations would account for the fact that you have this regional variability. So now, you now have an idea of kind of what the different observational scales look like. I will now quickly go through the variables. I will be moving fairly quickly, so there are lots more details given in the Lasso tech document, but I wanted to kind of give you an overview flavor. So in this plot, in this table, I'll be describing the variable. Using the nomenclature I just introduced you to, the point, local, and regional, and then I provided any specific comments. So for the first variable, we work with liquid water path. So this is the column integrated amount of liquid water above the sensors. I will note that we use in cloud, not domain averaged, which means that this is screen, zeros are not added in for clear sky values. This is only when a cloud is present. These are a point measurement because it uses both the ARRI as well as the microwave radiometer, which can only see directly overhead. And for those that are really in the know about the instrumentation, the default instrument is the ARRI-OE because it has the highest quality, particularly at low liquid water paths. But if the ARRI-OE is absent, we use the MWR RET field, which has greater uncertainties for values less than 50 grams per meter squared. Above those, the two values should converge. Next, cloud fraction. We have RSCL, TSI, or COGS. TSI and COGS were just briefly introduced in the prior slide. What RSCL is a combination of radar and LiDAR data. And basically, through that combination determines where clouds are located within the column. Since there are 3 different choices there, I'll be discussing on the next slide some of the ins and outs of choosing the appropriate observation. 2D time height cloud mask. Again, you can get this from RSCL by doing a time averaging of the fields that go over, or for COGS. Again, since there are 2, the differences will be discussed next. Cloud-based height, as I mentioned, is being obtained by the Doppler LiDAR network. Lifting condensation level. We do it at the central facility, as well as at across the region for the network that I just showed you. And then thermodynamic state variables at the surface from the central facility met station. And also at the central facility, we have access to a Raman LiDAR and area OE profile retrievals.
We're at 10 minutes, Andy.
What?
We're at 10 minutes.
Perfect, thank you. And then, and from these, we extract out the middle of the boundary layer, which is basically 500 to 700 meters, 500 to 700 meters. So moving along. Okay, so very briefly, we have these different cloud fraction sources. First, for area cloud fraction, we have the TSA, RSCL, and COGS. And just some comments. First, TSI and RSCL are available for all of the Lasso simulations. TSI can be contaminated by upper level cloud because it sees everything above it. So you have to be careful about when you use that data. RSCL it allows you to select for the lower part of the atmosphere. In this case, we use less than 5 kilometers, but we find that it tends to be pretty sensitive. And because it's a pencil beam observation, you need more time to sample. A trick that I've found that's very useful is that if you look at the time series of the cloud fraction from the TSI and the cloud fraction from RSCL, if you get good correlation, this is an indication that you have no upper level cloud influencing the TSI, and then I use the TSI cloud fraction variable. COGS is great when it's available, but as you get above about 50% cloud cover, it starts having problems because it can't see in between the cloud, the edges of the clouds. The 2D cloud mask, RSCL and COGS. This is an example of the plot, time versus height. Note that the height axis is two-toned. We expand the resolution in the lower part of the atmosphere, which is where we're interested in things. And what is shown here is the frequency of occurrence based on RSCL data plotted there in the color coding. If you look at the same day, but now using COGS, you'll see that in this particular case that they actually correlate quite well. There is and basically what you will find when you look across the spectrum of cases, there are many cases where RSCL and COGS are frankly just spot on. However, if they differ, RSCL tends to be deeper. And the reason that it's deeper is because it's susceptible to insects, insect returns. And there are some cases where you will find that RSCL is substantially thicker than what we get from COGS. So in my opinion, COGS is the best to use when it's available. However, just don't despair. There's a correction method that's being in progress by Christopher Williams that can potentially go back and correct some of the RSCL, historical RSCL archive. Okay, so finally, the data sets. The hourly averages are in Lasso Diags mod, and these are what are used for Lasso evaluation. We also make available the high frequency observation products, which are basically at native resolution. And these are specific products that we need to develop or for Lasso that are basically used to generate the hourly averages that are within Lasso Diag mod. You can read there what the different things are. They are all used within the evaluation package, except for the last one, which is the horizontal wind fields that we get from the radar wind profiler. These are actually used in our Lasso data assimilation, but not for evaluation. And then lastly, I mentioned to you that the COGS based evaluations, they actually just became available in the Lasso data discovery and will soon be included in the bundle browser as a download. So now for the model observation metrics, our diagnostics. So we have these observations and we have the model fields. First thing that we have to do is to get them on the same page so that we can do a fair apples to apples comparison. This means a couple of things. One of them is that we need to co-register the model and the observations, for instance, in time and with regards to the vertical grid. If there are instrument sensitivity issues, we want to sample the simulated variables in a consistent manner. This is something, for instance, we did with the liquid water path fields. And then ideally, when we can, we will even use the same algorithm, both on the simulated values as we did on the observations, such as we do with the LCL heights. And from this, we get a number of diagnostic plots that we make available. And what I mean by the diagnostic plot is simply that you can have a an observational comparable model variable plotted next to the observations. And very quickly, we generate heat maps, basically where you can look at the differences in the hourly differences between the model and the simulations. You can also then plot those hourly values and regressions. We plot the thermodynamic profiles for the available sounding times. We generate a number of time series, Taylor diagrams, which I will be explaining shortly, and 2D cloud masks, which I also will explain a little bit more. So all of these are useful information, but it's the last three that we focus on where we generate skill scores, meaning that we generate a single numerical value to help sort through the cases to find what you're interested in. So first one is the Taylor skill score. Shown here is a time series plot. Black is observations, color are the simulations of liquid water path versus time. You can then take those and generate what's called a Taylor diagram. For those of you who aren't familiar with it, basically what it does is it quantifies the level of agreement between the simulations and the observations in two variables. One is correlation, and the other is the normalized standard deviation. So if you have perfect agreement, you're going to have a dot down there at 1, 1. Okay. And then also from this, you can then compute a single Taylor score, such as that given in the upper corner. Next, you can then generate what we do is we generate a Taylor skill score plot. That Taylor skill that I just mentioned is plotted on the y-axis, and on the x-axis is the relative mean skill. And what can happen is that you could have a perfect Taylor score, but it can be offset, and you wouldn't know the difference. And that's why we include the relative mean score. So in this space, perfect agreement is up there at 1, 1. And the closer you are there, the better off you are. The concentric rings show values of equal skill score, starting at 0.9 going down to 0.2.
We're coming up on about 18 minutes, Andy.
Okay, good. All right. So then, so what we want to do then is then take this, we want to generate one number. And we do that by taking the Taylor score and the relative mean score and compute this value, where in this particular case of R is the liquid water path. And from this, you can generate a single value that is reflective of the level of agreement that you're seeing in the plot. A couple caveats. In this metric, 1 is perfect. High is good, low is bad. And what I mean by that is do not overinterpret the values. If you have values that are relatively close, let's say even within like 0.1 of each other, you do want to take a look at the additional plots to make sure that the metrics are telling you what you make sure that the visual inspection of the plots agrees with what you're looking for in the simulation. Next one is equitable threat score that we use to assess the 2D cloud mask. The top plot shows the time height frequency for R skull, similar to what we've seen before. Bottom line is the cloud fraction for a given simulation. You can then take these two and generate binary cloud masks that you can then compare, where green means that model and observations agree, and then you have misses and false positives, respectively, in red and blue, where a miss is a cloud that's observed but not simulated, or that a model is simulated but not observed. And taking all that together, you can then generate an equitable threat score, which is on the y-axis, and plot it versus its frequency bias score. Again, upper right-hand corner is perfect agreement. Generally, you will find that the ETS scores are a little bit lower, but they are faithful to how good to the level of agreement. They're faithful to the level of agreement. Similar to what we did before, we want a single value. We don't want to have to look at every single plot. And we basically use a very similar equation that allows us to generate a similar table that includes the 2D mask skill. And I'm just repeating here, same notes on interpretation. Do not overinterpret the numerics, but look for the higher values versus the low. The 2D mask skill is going to be used in future metrics. Finally, we have what we call multivariable net skill scores. So what I've described so far is a way that you can get a skill score for, let's say, liquid water path and cloud fraction, but it would be handy to be able to combine them. And this is how we do that. And we generate two special multivariable scores. The one is essentially the 2D cloud skill score. What it does is it combines the net skill score for the liquid water path and the net skill score from the TSI cloud fraction. So in this plot, basically what you're seeing is, how well are we doing with these two variables at the same time? And using the equation above, you can compute what's called the 1D cloud skill, which basically captures how well things are going in the terms of those variables. And you can see that you have a clear winner, if you will, or a lead candidate in number 5. You then have the total cloud skill. So what the total cloud skill does is it takes the 1D, so liquid water cloud fraction, and it grabs the 2D ETS skill score that I just talked about in the prior slide. So now you have, how well is the liquid water path, cloud fraction, and is the cloud in about the right spot? And this is the type of plot that you can get from that. And using the equation above, you can then get a total cloud skill. Okay, so the 1D clouds skill and the total cloud skill are things that you will find in the bundle browser so that you can search for your observations. So now my final section is going to address the Lasso bundle browser. It's available at the website given at the upper right-hand corner. And what it does is it enables interactive querying of the Lasso simulations and skill scores. It contains the diagnostic plots, so for quick reference to sort of see what the behavior of things look like. And then perhaps most importantly, it allows for ordering the data bundles. Given that this is a bit of an eye chart, I'm going to be breaking it into two sections, the upper and lower half for the sake of discussion. Okay, so for the upper part. Part A is where you select variables that are of interest. So this is where you select the dates, model configuration, and which measurement you're interested in particular. So, so far I've been working with liquid water path. It could be cloud-based height, etc. And then you click the big submit button at the bottom.
2-minute warning you requested.
Okay, cool. A little bit behind, but not too bad. For most of you out there, you probably will just want to select all, choose which measurement you're interested in, and then go into the date menu. If you choose all the dates, it'll be overwhelming. But if you scroll to the bottom of the date menu, you will find a select all button. Click that, it selects everything. Click it again, it clears everything, and then you can go ahead and click on whichever one you want. Next thing is that once you've selected that date, you will have access to the static plots that summarize general model behavior. And that's the heat maps, skill scores, and you will also have access to the GOES satellite image loop in the section B there. And then finally, the interactive, the right-hand side shows interactive plots showing the results for the measurement that you choose, for instance, liquid water path, and whatever choices that you had in C, which I'll be describing next. And so basically going clockwise, Taylor diagram, Taylor score versus relative mean, regression, and time series. For the lower half, it has two main components. First, and perhaps most interesting, is that you have slide rules. So measurement skill is the skill for that measurement that you chose. I've been talking about liquid water path, could be cloud-based slide, whichever one that you chose in part A. But then we have the multivariate skills, the 1D cloud skill, 2D cloud mask, and total cloud skills. And those were the ones that I described in the prior things. The nice thing is that you can take this and use the slider to move it to higher values. And the table will automatically update to only be showing those values that meet that criteria. Similarly, the interactive plots that were on the top half will also automatically update. So this is a very nice way of sort of cruising the data values to start finding which ones reach the criteria of interest. Very quickly, the tabulated values, tabulated results in this section, on the right-hand side, gives a lot of information. Again, remember that these are going to be updated depending on what choices you made for A and for the skill scores in item C above. First, you can save the table values. That's basically at the top of the page there. You have the summary of the simulation run configuration, and that's the I that's right next to each simulation. And that, of course, will match up with the metadata table that Bill mentioned before. There's going to be static plots of the diagnostics, the time series, Taylor diagrams, regressions, 2D cloud masks, and soundings that are going to be underneath the diagnostics tab. And then finally, ways to order the data. Currently, we have three. We have the config obs model, which Bill described earlier. We have the model, raw model output, which are the big files. And then we have the high frequency obs. It's a strong recommendation that you use Globus for file transfer. If you use FTP, sometimes it's possible for the files to get corrupted in the download. And we found that if you go to Globus, it always fixes that. All right. So then the final slide is the observation locations in the Lasso data bundles. Basically, there are three places where the observations are located. There's in the config obs mod file, the high frequency obs file, and the cogs file. You can see there the relative size per file of each of them. And basically the high frequency obs and the cogs files are fairly self-explanatory, but I do want to kind of give you a little bit of a roadmap in the diag config obs mod file. So this is the same image that Bill had, and where you will find the observations. The observations are posted in the same files where post-processed model output is. It's just a different field within that file. So that way you have both the model and the observations in the same spot, but this part's focused on the observations. Mod is where you get your 1D time series, and mod Z is where you get the time height profiles. If you have an earlier release, it possibly will not be mod Z, but mod 2D, but the files are the same, just the names are slightly different. Okay. There's also within this a plots directory. And Tammy set this up really nicely, that basically you run the HTML code in the directory that has a subdirectory of plots. And in those plots are the static diagnostic plots that we've just talked about. And when you run that code, this is what you get. You get a very nice display of those different fields. And note that there's a scroll bar on the first one so that you can scroll down to get to the other variables as well. The right-hand side is fairly, I think, reasonably self-explanatory. The first ones are the skill score output, either 1D and stat or stat 2 for the 2D. The heat maps that were described, and then a different plots.html file and subdirectory, which is focused only on the metrics plots. So that is everything that I had to say, and I'll be happy to take any questions you have. Thank you.
Thank you, Andy. We had a couple questions pop up I've basically answered. One was about precipitation affecting some of the observations. If you wanted to comment anything on that while people were thinking.
Well, I would say that in general, we are looking for cases that don't have any widespread precip. It is possible in the morning, for instance, for dew to be on, let's say, the hemispheric instruments, but it burns off fairly quickly.
Yeah. And then there's also a question about the macrophysical, well, actually the specific question is about microphysical variables like cloud droplet number, effective radius, things like that.
Yeah. Some of those are more specialized retrievals, and they are harder to do in the sort of routine framework that we have. And so because of that, some of these other things are not available. First off, cloud drop number concentration is very hard to retrieve. We actually have an ongoing project right now that will be doing that, but we're going to be starting with a maritime system where things are a little bit easier to handle. Arguably, there are some products with effective radius. It's not 100% sure. Based on prior experience, it's not clear that you're going to get a huge amount of variation in that variable at these sites. Again, because we are focused on non-precipitating shallow convection, you're going to be somewhat constrained in the dynamic range for that.
Those are all the questions that have popped up. And since we're running a tad behind, I think that might be a good time to transition the slide deck over to Tammy.
Okay.